Hello, everyone. Thank you for joining me today as we continue our conversation on this chapter, specifically on periodic table properties. In this video, we're going to talk about size, atomic size, and ionization energy. And so when we talk about an atom's size, it's a little bit tricky because as we learned about in the previous chapter, atoms don't have sharply defined boundaries because at which the electron distribution becomes zero because of the orbital shapes. So because of that, when we talk about the size of an atom, when it's being measured, we define that as half the distance between two identical nuclei. Okay, so that's how we define the size of an atom. The periodic trend for atomic size is shown here, and you can see that as you travel down a group, atomic size increases. And that sort of makes sense as you travel down a group. If you think about the electrons and the energy levels that they are in, the orbitals, you're going from 2s to 3s to 4s. You're adding electrons, you're also adding energy levels, you're adding shells, so the size of your atom is going to get bigger. So atomic size increases going down a group. It also decreases. It decreases going across left to right, going across a period. And that may seem a little counterintuitive just because you think, well, as you travel left to right across the periodic table, from element to element, you are adding an electron. So why doesn't the size increase as well? Well, when you're adding electrons, sometimes you're adding them to the same orbital. And if you remember from our previous video about effective nuclear charge, depending on the electron that you are talking about, the pull of that electron, the pull that electron will experience from the positively charged nucleus will increase. The effective nuclear charge will increase. So because of that, the atomic size decreases going across a period, going from left to right. So that's a trend, a periodic trend that you should know and be able to apply in problems, your homework, and for the exam. Now let's talk about the periodic trend ionization energy. So by definition, ionization energy is obviously energy, but it's how much energy it takes to remove a single electron from a gaseous atom or ion. By definition, the first ionization energy is taking that electron from that atom in its ground state, in its neutral state. As you continue to remove electrons singly from that species, you have different ionization energy values. Okay? So obviously the first ionization energy it takes to remove the first electron. The second electron is the second ionization energy, and so on and so forth. And so the trend that we are going to talk about with regards to ionization energy is the first ionization energy trend for an element, which is stated up here and shown graphically down here. When going down a group, top to bottom, ionization energy decreases. And you can easily see that, well, I'll just point it out here. So with helium, neon, argon, those are all in the same group 8. As you travel down that group, not only for that group, but all the other groups, ionization energy will decrease. When going across a period from left to right, the ionization energy increases. And you can see that also in this chart, but you also see that there are two exceptions that we're going to highlight. One of those exceptions involves beryllium, involves this little part here when going between beryllium and boron. So when going between groups 2 and 3, it's shown here, but also shown with magnesium and aluminum. When going between group 2 and group 3, it should increase, but it actually decreases. The second exception is when going from nitrogen to oxygen, so going from 5 to 6. So why do those exceptions occur? So if you think about with regards to the ionization energy trend between groups 2A or between groups 2 and 3, when you start removing an electron from group 2, you're going to remove it from an s orbital. Once you get to group 3, where boron is, now you have p orbitals, and those p orbitals farther away from the nucleus. There's also a little bit of repulsion by the s electrons in the group 2 elements, and so for those two reasons, the ionization energy for boron is smaller than for beryllium. Now let's talk about the exception for between groups 5 and 6 and why that is. And kind of easily seen if I'm looking at the orbital diagram. So if I'm going to remove an electron from nitrogen, it is going to come from that s orbital. If I'm going to remove an electron from the oxygen, it's going to come from a p orbital. So removing, if you remember, electrons, orbitals like to be half filled, all filled, or no filled. So for those reasons, the fact of where that electron is removed from, oxygen, or the elements in group 6, will have slightly lower than expected ionization energies than you would expect with the trend. So these are two exceptions that you should be familiar with when answering questions about ionization energy trend exceptions. In the next video, we will talk about another trend that's very similar to ionization energy, but it's called electron affinity.